Hi everyone, welcome to the third lecture of this module 1 where we are talking about the fundamentals of a measurement system. In the previous class, we started our discussion on static characteristics of an instrument and we were talking about the precision and accuracy. And in the series, we talked about different indications of precision, and then we thought that the precision is composed of two different characteristics, which are conformity and number of significant figures. Okay. So, a precision basically is composed of two characteristics as mentioned, conformity and number of significant figures, okay, particularly to show it mathematically. Okay. The basic understanding of precision, I think, was clear from the analogy of a football player. We discussed that if a football player is hitting area even outside the goal post at the same place or around the same place, it is called a precision. Okay. So, let us talk about the two characteristic of a precision or indication of precision, which is conformity and number of significant figures. Okay. So, what is conformity? Quantity actually called precision index basically describes the spread or dispersion of repeated results about certain central value. Okay. So, this will define our conformity. Okay. So, if I have certain value, say 3.6333 something like this. Okay. So, precision index basically will describe the spread or dispersion of the repeated data about this central value, that can be say 3.6334, 3.63331, something like 3.63328 like this. Okay. So, precision index describe the spread or dispersion of repeated result about the central value in the subsequent experiments. Okay. Now, high precision means that a tighter cluster of repeated result, while low precision indicates a broad scattering of the result. So, tighter the result around the central value, we can say that it has a higher precision. Okay. Similarly, if you talk about significant figures we all know that it convey the actual information regarding the magnitude and the measurement precision of a quantity. Okay. So, more the basically significant figures, the greater the precision of the measurement is. Okay. So, this is basically the mathematical indication of precision in several instruments. We will talk about this when we will discuss the actual results from a instrument in more detail. Okay. We are just overviewing the static characteristic so that we are on the same page when we talk about different instruments. Okay. The next static characteristic of an instrument is the reproducibility. Okay. So, it is the degree of closeness with which a given value may be repeatedly measured, or the closeness of the output reading for the same input when there are changes in the method of measurement, the observer is changing, the measuring instrument itself is changing, the location of measurement is changing, the condition of use is altered, and the time of measurement of course has changed. So, if you have say some of the parameters, even one of the parameter changed, okay, and then you see the degree of closeness with which a given value is repeatedly measured, okay, is reproducibility. Okay. So, a perfect reproducibility means that the instrument is drift free, there is no drift. Okay. When I say there is no drift, means that with a given input the measured value do not vary with time. Okay. So, let us try to understand this with an example. Okay. Say if I have a ammeter, okay, there is one ammeter which is monitoring a current across one sensing device, for example. Okay. So, I am trying to measure the current across this continuously. Okay. No drift means that with a given input, the measured value do not change with time. Say measured value is say 10 micron. Okay. So, the ammeter will show continuously a 10 microamp. Okay. Now, say if this sensor is loaded. Okay. Now, if this sensor is loaded by some external load, okay, and say because of that the output current here altered. Okay. Now, if you measure it continuously, there will be change in the measured current. Okay. Now, this from the I was expecting this value, but it has gone to this value. So, this is the drift in a result. Okay. So, now I can say that this result is not reproducible. Okay. This can be, as I have mentioned, due to external effect, or it can be due to some internal effect. Okay. Whatever sensor it is, say if the sensing material is degrading, for example, okay, or there can be other issues like the transducer is not functioning properly, okay, or there can be other issues because of which this drift can happen. Okay. And if I classify the drift in an instrument, it can be categorized under 3 different categories. Okay. I can have a zero drift, there can be span drift, which is also known as sensitivity drift. Okay. And then the third type of drift is zonal drift. Okay. So, let us try to understand these 3 drifts. Okay. First is zero drift. Okay. In the zero drift, what happens is the whole calibration of the instrument is basically shifted. Okay. You just see this transfer characteristic of a instrument, you have this input versus output, and this was the normal characteristic, or I can say nominal characteristic of a instrument. Okay. Now, the characteristic has shifted to this position. Okay. And this is basically, if you see the complete shift from the nominal characteristic. Okay. So, this is known as, this is actually the characteristic with the zero drift. Okay. So, the whole calibration has gradually shifted in this case. Okay. There can be various reasons for this shift. This can be due to slippage, due to permanent set in a instrument. Okay. Like say if the instrument is using some spring based component, okay, there can be a permanent set in that particular spring. Okay. Or it can also be due to certain undue warming which is not desired. It can be due to heating effect in the electrical or electronic circuit, or certain component can heat up. Okay. Because of these things, this zero drift actually occurs in a, or it sets in a instrument. Okay. Mostly these devices can be prevented by a zero setting. Okay. Then another kind of drift is the span drift, or we also call it sensitivity drift. Okay. So, in this there is a proportional change in the indication all along the upward scale. Okay. This is 2 different example of span drift or sensitivity drift. Okay. Since if you see, it appears along the complete span of the sensor, the name is derived. Okay. So, this is the nominal characteristic, and this is the characteristic with span drift. Okay. So, this is the nominal characteristic, and this is the span drift in a instrument. Okay. Now, this span drift can occur also with the zero drift. Okay. So, both can occur simultaneously. So, this is a typical example of a transfer characteristic of a instrument, where this is the nominal characteristic, and this characteristic shown here also has a zero drift. If there was only zero drift, the output was expected something like this. Okay. Now, if this characteristic has zero drift along with the span drift, so the drift occurs something like this or something like this. Okay. So, this is actually characterized by the proportional change in the indication in the complete scale of the instrument. Okay. Now, if the drift occurs only over a portion of a span and not in the complete span of the instrument, this is known as zonal drift. So, in that case you can expect that, say, this is only in certain area, say in this zone or in this zone, okay, not in the complete span or in the complete input range. Okay. So, that is a zonal drift. I hope that the three different drifts is clear to you, and this is actually directly related to reproducibility, as we have seen that a perfectly reproducible results means that there is no drift in the instrument. All right. So, now, once the concept of reproducibility is clear to us, let us move to another static characteristic, which is the repeatability. Okay. So, the closeness of output reading when the same input is applied repetitively over a short period of time or a small range of time, but there are certain conditions like with the same measurement condition, same instrument and the same observer. It should be also the reading has to be taken at the same location, and the conditions also is maintained in the similar fashion which was there in the previous reading. If you see, these conditions were not there in case of the reproducibility. Okay. So, the closeness of output reading when the same input is applied repetitively over a short period of time. If you see, now this short period was not there in case of reproducibility. Okay. So, this is one example of transfer characteristic of an instrument when you apply the input for a short period of time, okay, with all these conditions same, like same measurement condition, same instrument, same observer, the same location and same conditions or at least similar conditions, okay, and then we check that if the results are repeatable or not. Okay. So, this is a typical graph showing the plus minus repeatability of a instrument. Okay. Then another characteristic which is sometimes very crucial, particularly for the electrical instruments, is the tolerance. Okay. So, it is the maximum deviation of a measurement or the manufactured component from some specified values. Okay. So, usually this maximum deviation is given by the manufacturer itself. Okay. So, like say I have a voltmeter. Okay. The voltmeter usually will come with the tolerance limit. Okay. So, every voltmeter, ammeter, wattmeter, whatever you take will come with tolerance limit, and this is mostly specified in the specification sheet of a instrument. Okay. Then we have range and span of a instrument. Okay. So, this is very simple. The minimum and maximum value of a quantity that the instrument is designed to measure is known as range, okay, or the span. So, if I have to find the span, it is basically the maximum input that it is made for, okay, minus the minimum input it can take. So, that max minus mean will give me the range or the span. Okay. Then another static characteristic is the linearity of a instrument. Okay. It is always desirable that the output reading of the instrument is linearly proportional to the quantity which is being measured. It's desired mostly because if the device is linear, okay, the predictions for the forecast of the unknown quantities become very easy. Okay, let us try to understand this with an example. Okay, so I have a transfer characteristic. Okay, so this is output versus input. Okay, and say my device has been found to be linear. Okay, and say in this range it has been tested. Okay, and the span is something like this x1 to x2. Okay. Now, if there is the input value x3 and x4, this is x4, this input is x4 and this is x3. Okay. Now, this device has been designed to measure between x1 and x2. Okay. Now, I want to measure this x3 and x4. Okay. The linear characteristic of the device can be extrapolated in these two ranges. Okay. Because this is linear, I know the slope, I can find this by extrapolation techniques. So, both output for the x3 say it is y3 and for x4 say it is y4 can be found by this extrapolation. Now, if it was not linear, in place of this it was non-linear. Okay, the characteristic was something like this. Okay, in this case the extrapolation becomes very difficult. Okay, now I don't know that what will be the output when the input is x4 or say x3 in this area. Okay, because if this is non-linear, it can be like this also in this range, I don't know. Okay. So, the instrument is desired to be linear. Okay. Now, if I understand this linearity, the non-linearity is just opposite to that. Okay. So, non-linearity is then defined as the basically maximum deviation of any of the output reading from the straight line or the linear part. Okay. So, mostly this non-linearity is expressed as a percentage of full scale reading. Okay. So, non-linearity mathematically can be found by this equation as maximum deviation of output from the idealized straight line divided by the full scale deflection multiplied by the 100. Okay. So, this is the say output reading versus measured quantity curve. Okay, and this is the straight line, the deviation from this straight line. Okay, in a curve. Okay, I can find the non-linearity of the device. Okay. Now, the next characteristic is the sensitivity, again which is very important, and we will see that most of the instrument that we are going to talk in the next module are compared based on their sensitivity, particularly if the user know their desired application. Okay. So, sensitivity is a measure of the change in the instrument's output that occurs when the quantity being measured changes by a given amount. Okay. Mathematically, it can be found by dividing the scale of deflection with the value of the measurement producing the deflection. Okay. So, when a calibration curve is linear, as you can see here, the sensitivity of the instrument by the previous definition can be defined as the slope of the calibration curve. Okay. So, if the output is q naught and input is q I, okay, the change for two different points, if it is in the output it is del q naught and for input it is del q I, the sensitivity is defined at del q naught by del q I, which is basically if you see the slope of the calibration curve. Okay. Now, the sensitivities varies with the input for a non-linear device. Okay. And for this you can find the sensitivity of a non-linear device in different regions. Okay. So, the sensitivity of this non-linear device in this particular range, okay, this or you can say I am using a word zone. okay, because we have seen the zonal drift. Okay. So, similarly the concept of zone I am bringing here. Okay. The sensitivity in this zone and sensitivity in this zone can be different, and that is also perfectly fine that this device has different sensitivity in different regions. Okay. Now, another important static characteristic of a instrument is threshold. Okay. So, when the input to an instrument is gradually increased from 0, the input must reach a certain minimum value before the instrument's output changes become large enough to be detected. Okay. So, means that the minimum level of input at which the output or the instrument starts responding is known as the threshold. Okay. So, let us see one example. Okay. Now, I have say output versus input for two different instruments, say instrument 1 and then instrument 2. Okay. Now, both are say is measuring say current or say temperature. Okay. Say I am talking about a transducer which is measuring the temperature. Okay. Now, of course, say input is in degree Celsius and output say it is giving in terms of certain resistance change. Okay. When you increases the input, it will not immediately start showing you the result. Say at 4 degrees Celsius or say at 2 degrees Celsius, it started showing the output. Okay. So, the minimum level of input which is required for having certain output change is known as threshold. So, for this case, this 4 degree or 1 degree will be the threshold. Now, in this case, if I want to compare it based on threshold, say if started responding at 8 degrees Celsius or so. Okay. So, if I compare this, the threshold of this particular device is much better as compared to the second one, right. So, I hope the concept of threshold is clear to you. Mostly this threshold is expressed either as an absolute value as I have just mentioned, or sometime it is also expressed as a percentage of the full scale reading. All right. Then one more characteristic of a instrument is a resolution. Okay. And sometime it becomes very crucial for an end user to pick a particular instrument. Okay. So, resolution is the smallest increment in the input that can be detected with certainty by an instrument. Okay. So, if I have to give an example, okay, say again we will take the example of two different sensors or two different instruments, say which are trying to measure now current. Okay. Now, say if this instrument instrument 1, okay, gives say there are 3 different instances where I have to measure the or 3 different experiments where I have to measure the current. Okay. Now, for instance 1, it gives current say instance A, it gives a current value of say 3.5111 say microamp. Okay. For instance B, it gives me a value of 3.5111. Okay. And again for C, it is giving me a value of 3.5111. Okay. So, in all the cases, it is giving me a value of very nice good significant figure data like 3.5111. Now, for the sensor 2, for these 3 different instances, okay, the measured values are 3.5111. Okay. Then another is 3.511132 and another is 3. Say this is say 00. Okay. 3.511131. Okay. Now, if you see the second sensor is able to resolve in the much better fashion as compared to the sensor 1. Okay. So, the current value of 3.511132 is given by 3.5111 in case of the instrument 1. Okay. All right. Similarly, if I give an example of a sensor, okay, like the sensor, for example, is measuring certain chemical concentration, okay, and this chemical concentration is say in the range of ppm. Okay. Now, this is able to measure, say this is say first data is of 40 ppm, okay, this is say 50 ppm, this is sensor 1. Okay. Now, I have another sensor, okay, this is giving me 40 ppm, this is the data for 45 ppm, this is the data for 50 ppm, right. So, in this case, if you see, it was not able to resolve in between anything, okay. Either it is giving 40 ppm and after that it is giving 50 ppm, but what if I want to measure say 45 ppm, okay. So, that is why the definition of resolution I mentioned, the smallest increment in the input or the quantity which is being measured, that can be detected with certainty by an instrument is called the resolution. All right. So, sometime resolution is very crucial factor or characteristic for an instrument. Okay. Next characteristic that we are going to talk is the hysteresis effect. Okay. So, basically it is the non-coincidence between the loading and unloading curve of a transducer or as a instrument. Okay. This is mostly expressed as a percentage of full scale input or output reading. Okay. So, the example can be, I mean, all the transducers, a spring based instrument or a direction dependent friction or say magnetic field hysteresis, all these things are an example of a hysteresis effect. Okay. So, hysteresis as I have mentioned is the coincidence between the loading and the unloading effect. Okay. Mathematically it is the maximum difference in the output when the value is approached with an increasing and a decreasing concentration range of say if it is a sensor or if it is a transducer. Okay. So, this is one example where the sensor is trying to measure some concentration from 50 ppb to 5.45 ppm, okay, and then again back to 50 ppm. So, this is nicely done dynamic plot. Okay. This is the dynamic plot. If I convert this dynamic plot into this static plot, okay, where I plotted this concentration 50, 100, 500 like this, okay, and I see that when the concentration was increasing, how the resistance is behaving, okay, and then going back from the top to this lower concentration or from 5.45 to again back to this lower concentration, and then I would like to see that are they coinciding over each other. Okay. If it is not, okay, means that the sensor or the transducer has a good amount of hysteresis. Say for this data I can say that in the lower concentration range the transducer has higher hysteresis as compared to what it has in the higher concentration range. Okay. Now, another characteristic which is very important is the dead time and dead zone. Okay. So, dead time is defined as the time required by a measurement system to begin to respond to a change in the measurand, and dead zone is the largest change of the input quantity for which there is no output of the instrument. Okay. And mostly this is around the zero value of the instrument. Okay. So, like this is one example of dead time and dead zone. Okay. So, this was the input measurand and output has started from here. So, this is the dead time. okay, when there was no output, and this is the dead zone of the input. Okay. Then the loading effect is another characteristic or static characteristic of a instrument. Okay. This is the basically the incapability of the system to faithfully measure, record or control the input signal, which is basically measurand in undistorted form. Okay. So, the ideal situation in a measurement system is when an element is introduced into the system, the original signal should remain undistorted. Okay. The purpose of this element can be anything. It can be for signal sensing or conditioning or transmission or say detection. Okay. If there is certain changes, okay, means that it is causing the loading effect to the measurement system. Okay. So, that is why you will see that the ohm meter or say voltmeters, for example, is connected in the parallel of any circuit, okay, while ammeter is connected in the series. Okay. So, this is mostly done to avoid any loading effect. Okay. We will talk about this when we will discuss the analog instrument in more detail. Okay. Another static characteristic which is very important if we are trying to understand this measuring instrument is the noise. Okay. Noise is basically an unwanted current or voltage which mixes with the main signal in an electrical or electronic circuit. Okay. And mostly we use SNR to characterize this. Okay. So, the signal to noise ratio or the SNR is defined as the ratio of the power of a desired signal to the power of the background noise that distorts or masks the signal. So, if I have to calculate the signal to noise ratio, which is kind of indication factor for the domination of noise in a signal, okay, is given as the ratio of signal power to noise power. We know that this power is directly proportional to the voltage square. So, signal to noise ratio is also given as signal of interest expressed in volt square divided by unwanted noise expressed in volt square. Okay. The noise in the output is broadly of three different types. The one is the generated noise, okay, which is generated inside a measurement system. We will discuss that. Okay. Then conducted noise, okay, and the radiated noise. Okay. So, we will talk about these three different noise, the generated, conducted and radiated noise in the next class. Thank you for your attention.